Today I am going to help you understand how reactions happen by giving you an overview of reaction mechanisms. A reaction mechanism is a step-by-step picture of how a reaction actually happens, showing the bonds breaking, new bonds being made, and the movement of electrons during this process. Now, conventionally, when you look through your A-level textbook, reaction mechanisms are taught in a series of boxes under solitary confinement. We learn how alkenes react, and then maybe half a term later we will have a look at how alcohols react. And I feel as a result of that, students learn this parrot fashion and they don't really get a grip on the underlying principles. The problem with this is that when they're thrown a curveball, they aren't able to easily adapt their understanding to solve the new problem. So how do reactions actually happen? Well, most of them take place via a series of steps. We start with our reactants. We form either one or more intermediates, and then they go on to produce our product, and often co-products or byproducts as well. Now, in organic chemistry and carbon-based chemistry, these intermediates are very often carbocations and occasionally carboanions. We come across the carboanions very rarely at A level. So what is a carbocation? What is a carboanion? Well, cations are positively charged. So it might look like so, with a positive charge on the carbon atom, and obviously a carboanion, we have got a negative charge on a carbon atom. And these are short-lived. We can detect them via a number of spectroscopic measures, but we can't actually isolate them. You can't go and get a vial of carbocations off the prep room shelf. An R group is shorthand for alkyl. So it might be methyl, it might be an ethyl group. The possibilities are endless. We form a carbocation by breaking a carbon something else bond heterolytically. So let's have a look at this. For example, if I were to take this molecule here, we can have a hydrogen, we'll have another methyl group down there, and we're going to have a bromine. In heterolytic bond fission, both the shared electrons in the carbon-bromine bond move onto the bromine atom when that bond breaks. So this is heterolytic bond fission in action. Note that I am using a curly arrow to show the movement of the electrons, and it's a double-headed arrow because I'm moving a pair of electrons. They're moving onto the bromine because bromine is more electronegative than carbon. So the result of this bond fission would be to form this carbocation and a bromide ion. Carbocation intermediates are very short-lived because the positive charge leaves them open to attack by a nucleophile, a hydroxide ion, for example. Now, if we were to look at the electronic structure of a hydroxide ion, we've got the shared pair of electrons between the oxygen and the hydrogen. Oxygen has 6 electrons of its own, and it's negatively charged because somewhere along the line it picked up another electron, maybe from sodium, for example. What this gives it are 3 lone pairs, one of which it can use to make a bond to an electron-deficient carbon atom. So we would draw a curly arrow to show the movement of electrons, and arrows always show the movement of electrons from where they start to where they finish. And we can use this pair of electrons to form a bond between the oxygen and the carbon. And this would be our product. So we've gone from a haloalkane via a carbocation intermediate to an alcohol. This species here is called a nucleophile. And a nucleophile is a negatively charged ion, or perhaps a neutral molecule, that's able to donate a pair of electrons to an electron acceptor. So this positive charge means that this carbon is missing electron, it's electron deficient, so it can accept a pair of electrons, and we form a new covalent bond between the carbon and the oxygen. So what else could make a nucleophile? Well, other ions, negatively charged ions, we've got the chloride ion, we've got the bromide ion, for example, might be a neutral molecule. So ammonia, for example, NH3, because nitrogen has got a lone pair of electrons that it could use to donate to an electron deficient carbon and form a covalent bond. Anything that ammonia can do, an amine can do. So an amine is where we replace one or more of the hydrogens with an alkyl group, an R group. So that amine there, methylamine, would also be able to act as a nucleophile. Water can act as a nucleophile because the oxygen in water has two lone pairs of electrons, one of which it could use to make this new covalent bond with an electron deficient carbon. The key here is, in terms of thinking about nucleophiles, so let me write that out again, is that nucleophiles are always on the attack because they are seeking out a delta positive carbon or a positively charged carbon atom with which they can make a covalent bond. So phile means to love, as in the opposite being phobia, to hate, and they're loving a nucleus. A nucleus is positively charged because of the protons in it, so they themselves are going to be negatively charged, or as I've said, have got this lone pair of electrons. The strength of a nucleophile depends on its ability to donate its pair of electrons to make that covalent bond. So we find, for example, that hydroxide ions are stronger nucleophiles than water, because in a hydroxide ion, our oxygen's got three lone pairs of electrons. It's easier to donate one of them. Compared with water, oxygen's got two lone pairs of electrons. Similarly, an amine, so R being an alkyl group, is going to be a stronger an electrophile than, say, an alcohol. In both cases, the nitrogen or the oxygen is using one of its lone pairs, in the case of oxygen, its lone pair in the case of nitrogen, to make that covalent bond. Nitrogen is less electronegative than oxygen, so it's holding on to its lone pair less tightly, which means it's going to be easier to donate, easier to form a new bond with a carbocation. Similarly, in terms of anions, we would see that an iodide ion makes a stronger nucleophile than, say, a fluoride ion. Again, because in an iodide ion, it's a much, much bigger ion, and so it's far easier to use its lone pair of electrons on the far outer rim of that ion to make a new covalent bond than the fluoride ion, which will be holding on to its electrons very, very tightly indeed. The opposite of a nucleophile is an electrophile. Electrophiles are electron-loving, so they are positively charged ions or neutral molecules that can accept a pair of electrons from an electron donor to form a covalent bond. So let's have a look. A positively charged ion, well, that might be a carbocation, for example. So a carbocation is a very strong electrophile. That positive charge is strongly attracting electron donors. We saw that our electron donor is essentially a nucleophile, using a lone pair of electrons to make a new covalent bond. It doesn't have to be a positively charged ion. It could be delta positive carbon in our molecule. So, for example, if we were to start with a haloalkane, let's start with a chlorine atom there. Due to inductive effects, we know that the electrons in the carbon-chlorine bond are drawn towards the chlorine and away from the carbon. And the more electronegative this atom is, the further the electrons are going to be drawn away from the carbon, and the more delta positive this carbon is going to be. As a result, that carbon opens itself up to attack by a nucleophile. So in this particular mechanism, let me just, let's just start with a fresh molecule. In this particular mechanism, what we find is that the delta positive carbon is attacked, and that attack precipitates the leaving of the chlorine. The carbocation is so short-lived, it's almost one swift homogeneous step. So what we're saying here is the hydroxide ion attacks this carbon because this carbon is delta positive, the chlorine is delta negative. Chlorine leaves, we have heterolytic bond fission, taking both electrons with it, and the chlorine is indeed called a leaving group. And as I said, this is all kind of happening in one homogeneous step. We then have methyl group, new bond to the hydroxide, forming our alcohol, and our chloride has left. This is an example of an entire reaction mechanism going all the way from reactant to products. It's a substitution reaction because the chlorine is substituted for hydroxyl group. We go from haloalkane to alcohol. And it's nucleophilic substitution. So let's write that out. Nucleophilic substitution. So we've explained the substitution. This is where things can get a little bit confusing because clearly we have both electrophile and nucleophile, and we do this in many of our mechanisms. But the name just represents or describes the first step in our reaction. And the first step in this reaction is a nucleophile attacking a delta positive carbon atom. Let's have a look at another type of electrophile. In this case, the electrophile is not our organic molecule, it's the other reactant in this reaction, hydrogen bromide, because hydrogen is delta positive and the bromine in hydrogen bromide is delta negative, bromine being considerably more electronegative than hydrogen. This delta positive hydrogen is electron deficient enough to get itself attacked, and it's attacked by the pi electrons in a carbon-carbon double bond. So let's remind ourselves, in a carbon-carbon double bond, we've got a sigma bond between two carbon atoms, and then we've got this area of electron density above and below the plane of the carbon-hydrogen skeleton, and that is our pi bond. So it's the pi bond electrons that can be used to go out and attack the delta positive hydrogen. This causes bromine to leave, again heterolytic fission, both the electrons go to the bromine. So we end up with an intermediate hydrogen. So the pair of electrons in this from this pi bond are now being used to make a bond between one of the carbons and the hydrogen that was in HBr. Remember, the molecule is still intact because I haven't broken the sigma bond between the two carbon atoms. However, my second carbon atom is now positively charged. I've formed another carbocation. We have an electron deficient carbon because it's lost its pi electron. Its pi electron has just been co-opted to make a new bond between the other carbon and the hydrogen. And I hope you can see what's likely to happen now. When the bromine left, it took both the electrons, so it's a bromide ion. This bromide ion can behave as a nucleophile and attack the positively charged carbocation using its lone pair of electrons to form a bond between the bromine and the carbon. So we're going to end up with our product. We're going to go from alkene to haloalkane. Now this type of reaction is called an addition reaction because I've taken two molecules and added them together. And it's electrophilic addition because the first step in this reaction mechanism is the attack on the electrophile by the pi electrons in the double bond. So this is electrophilic addition. So that is a basic overview of a reaction or a couple of reaction mechanisms. In your notes, you'll need definitions for electrophile and nucleophile. You can use either the syllabus statements or the textbook. You need to be able to recognize when a reaction is a substitution or an addition, and whether it's electrophilic or nucleophilic. Remember, that is all about this first step in the reaction mechanism. And once you've got your head around this, and I suggest very strongly you check out the next video in the series on inductive and mesomeric effects in reaction mechanisms. It's one of those topics which isn't specifically covered either by textbooks or the syllabus statement at A-level, but it crops up everywhere, even at A-level. You're kind of expected just to take it at face value, and I think, as always, it's really important that you have a proper understanding in order to make sense of everything. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.